Now we heard the talk of Professor Suzanna Doshla.
Thank you. Thank you for inviting me to this interesting conference. And let me to share the screen. So I will speak about asymptotic proximity to higher order nonlinear differential equations. And as I said before, this is the joint research with Irina Astashova, Miroslav Bartušek, and Mauro Marini. So here is the overview of my talk. First, I will give a short introduction, then I will speak about asymptotic proximity, and then about strong asymptotic proximity. So let us consider the higher order nonlinear equation of this form, equation 1, where the functions on the left side of equation a sub j are continuous for on the half line 0 infinity. The function r on the right side is continuous, and the nonlinearity is the power function, so equation of the Emden-Fowler type. And let us assume that the lambda is bigger than 0, and let us consider equation of order n, where n is bigger or equal 3. Our problem is to study the existence of unbounded solutions with polynomial or non-integer power law asymptotic behavior. And we study equation 1 as a perturbation of the linear equation. So where on the right side of equation we have the 0. So we study equation, let us say blue 1, as a perturbation of equation 2. And in addition, we study the special case of equation 1, where the operator on the left side is just the order n and n minus 2. The derivative are n and n minus 2. And this equation is studied as a perturbation of the linear equation of the form equation 4. So let me to introduce what is the the definition of asymptotic proximity. So we say that equation 1 is in asymptotic proximity to linear equation 2 if for any solution y of 2 there exists solution u of the original nonlinear equation, such that for large t we have this equality. So it means that solution of the nonlinear equation can be expressed as a solution of the linear equation multiplying by the function near 1 plus some functions epsilon. And this equality holds for all I from 0 to n minus 1. And so the function delta and epsilon are continuous and tends to 0 at infinity. This notion can be set in the stronger way. So equation 1 is said to be in strong asymptotic proximity to equation 2 if for any solution y there exists solution u of the original equation, such that for large t we have this equation. So it means that the difference between u and y is some function epsilon, where all these functions epsilon are of bounded variation and tends to 0 for large t. So this is two crucial notions, asymptotic proximity and strong asymptotic proximity. And shortly about the history of this problem. Such problems have been studied, but usually in terms as asymptotic equivalence of solutions of some equation and of equation which is perturbated to the given equation. Now let me recall that the work of Sobol and Vanokhi-Kuradze in this work, there were studied the existence of solutions and their derivatives with polynomial growth. And the main results of Vanokhi-Kuradze can be formulated in terms of asymptotic proximity in the following way. For the linear equation of this form, we have that in order to be in asymptotic proximity to equation n order equals 0, is sufficient, and for the sign constant function r, also necessary that integral of this integral is convergent. So if roughly speaking, if the function r of t is small in this sense, then we have, and if r does not change sign, we have necessary and sufficient condition that these two equations are in asymptotic proximity. Other results in this field are results of Irina Astasheva. There are several results in this field, usually formulated in terms of asymptotic equivalence. More details is given in the book. This is the last reference in the book, Qualitative Properties of Solutions to Difference Equations and Related Topics of Spectral Analysis. And with another contribution is by Miroslav Bartušek, Mariela Čeky, Mauro Marin, and myself in these two papers. So it's roughly speaking about the history. Now our results about asymptotic proximity for equation 1. So let us consider a nonlinear equation of an order, let us say full with all terms. And we want to prove the existence of n-parametric set of solutions of equation 1 with a polynomial growth. And this equation is studied as a perturbation of this linear equation. Our main result is the following. Assume that the nonlinearity satisfies the condition that lambda is bigger than 1. So we have superlinear equation. And assume that the function a sub j are small, so in this sense that integral is convergent, or this integral is convergent. And the function r of t on right-hand side of equation is small in this sense for some integer m, from 0 till n-1. Under these two conditions, for any non-zero constancy, there exists a solution of equation 1 with this asymptotic behavior. It means that the limit tends to the constant c for all j, for all integer j from 0 till m, and from j from starting n+1 till n-1, the derivative tends to 0. So this is the main theorem, and if we take in this theorem the integer m equal n-1, then we obtain, so lambda is bigger than 1, a is small in this sense, and the condition on the function r of t reads by this way. then equation 1 is in asymptotic proximity to linear equation 2, which means, according to the definition, that for any solution y of 2, there exists a solution of the original equation with this equality, where the function delta and epsilon are continuous and tends to 0. So this is the main result for full equation 1. And as a special case, so from here we can see theorem 1 as a generalization of the theorem of Van-Oki-Kuraze for linear equation. And theorem 1 also extends the result of Irina Astashova from Mathematica Bohemica 2010. In this paper, there is given more strong result under more strong restriction on the function A. Very shortly, let me just to give some, let's say, the main idea of the proof. So equation as a first step, our equation is written as a two-term equation with this conjugate operator in the canonical form. So in more details, we have the linear differential operator from left-hand side of equation. So let us call it L. So such operator is represented in neighborhood of infinity as the composed operator of this form, where B sub j are the first order operators, and each small bj are smooth function which tends to 1 for t tending to infinity. So as a first step, equation is written as a two-term equation. Then it is introduced the set of operators in the convenient spaces and the composition operator F. And using very precise estimations, it's possible to prove that there exists a unique fixed point of this operator. I will not go to the details because it requires a lot of auxiliary results and estimations. So this is just about, let's say, the main idea about the proof. Now about strong asymptotic proximity. Let us consider higher order equation as before, but on the left side we have only two terms, and we study this equation as a perturbation of such linear equation. And let us and for such special form of our equation, we study the property of strong asymptotic proximity. Let me recall that equation 3 is said to be in strong asymptotic proximity to linear equation 4 if for any solution y of 4 there exists solution u of equation 3 such that for large T we have this equality for all index I from 0 to n-1, and functions epsilon are of bounded variation and tends to 0. Since we have equation in special form, so we can let us say we can give another kind of results and estimations, which comes from second order equation. So assume that the corresponding second order linear equation is non-oscillatory, and denote H1, H2, the basis to independent solutions of this equation. Then the space of solutions of linear equation has the basis which consists of the function, the polynomial t to j, and moreover the function, let us call it gamma 1 and gamma 2, which are of this form. So the functions gamma 1, gamma 2 are constructed using the solution of second order linear equation by this form. So we can describe the basis of the perturbative of the equation of the linear equation. Now for the theorem, let us introduce the following notation. Let us put IQ 0 if the function q is small in the sense that this integral is convergent. And in the opposite case, let us put the symbol IQ equal 1. Then we have the following result. Assume that the second order linear equation is non-oscillatory, and for some real number m from the interval 0 and -1 including, this integral is convergent. Here the index I the number I sub q is here. So it is 0 if q is small, let us say, and is 1 if we are on the border between oscillation and non-oscillation, let us exactly speaking. So under this assumption, for any solution y of the linear equation such that it is bounded by the function Tm. So here is this is the classical notation, is bounded by the polynomial Tm. There exists a solution U of the linear equation satisfying this equality for large T, and the function epsilon are of bounded variation and tend to 0 for large T. Let us compare, let us stress that here in this theorem, in comparison to the previous theorem, the number m can be real, so it's not necessary to have the polynomial growth, but in general non-integer power law, let us say, behavior. And as a corollary, if we take again the number m, the border limit, and -1, we obtain that under this condition that the function r in the equation is small in the sense that this integral is convergent. Then equation 3 is in strong asymptotic proximity to linear equation 4. So it means that solutions of equation 3 can be expressed in this form using the function gamma 1, gamma 2, and polynomials of the degree less or equal n minus 3, and function epsilon are of bounded variation and tends to 0. So this is the main result for the strong asymptotic proximity. And idea, let me give just the real idea of the proof. We use again topological method, but completely different. Is the following. So let Y be a solutions of linear equation 4. Because we assume that the solution Y is bounded by the polynomial T to M, there exists L with this inequality. And let us take T0, let us say sufficiently large that we have this estimation. Now we construct on interval T0 infinity. So this is the fixed interval. T0 is determined by this inequality, by this condition. We construct the sequence of functions U sub k defined by this way. So the first term U1 is equal just solution Y of t. And now U sub k is defined as Y of t plus this term where we have, so this is, let us say, from the right hand side, this is the Wronskian for the second order equation, and the number, the sequence capital T sub k is defined by this way. And this is so this is the integration is from sigma to capital T sub k, and the outside integration is from small t to capital T k. D is connected with the number connected with the second order linear equation. I don't go to the details, but let us say the idea of this topological approach is the construction of this sequence. And it's possible to show that such functions satisfy the nonlinear equation, and it's possible with very precise estimation to prove that the sequences of U sub k and their derivatives are uniformly bounded and equicontinuous on each finite subinterval of interval T0 infinity. So by this way, we construct the required solution view of our equation 3. Now let us consider the special case of equation 3, where the function qt on the left side is epsilon over t square. So we have such nonlinear equation, and the related linear equation then is of this form. And epsilon is from 0 to 1/4. This condition comes from the fact that the corresponding second order linear equation, this one, is non-oscillatory for such epsilon. And what is important, that we can calculate the solutions of second order linear equations, which is the functions t to me1, t to me2, where me1 and me2 are given by this way. So here we can say more, because we can calculate the growth of solutions of second order linear equations. Since we can calculate solutions H1, H2, so we can also calculate the growth of an order linear equation, this one. So this equation has a basis of solutions consisting of polynomial t to j, and the function gamma 1, gamma 2. But in this case, we can calculate the growth of these functions, which is the growth is t to beta, where beta is defined by the order of equation n and epsilon. So we can make this calculation. So the second solution, gamma 2, is bounded by the by the function t to gamma, where gamma is defined by this way. So for this special case of equation, we obtain the following result: that under assumption that the function a from equation is small in this sense, where the number gamma is defined by this way, then equation 7, here is the misprint, then equation 7, our equation blue, is in strong asymptotic proximity to linear equation 8. So it means that equation 7 has n-parametric set of solutions U, which can be expressed by this way. So here is, so it is the linear combination of the function gamma 1, gamma 2, where we know the precise growth, not necessarily polynomial, but in general non-integer power law growth. Qt plus Qt is polynomial of the degree n till n-3, and some small function with bounded variation and tending to 0. So this is the application of results for this special kind of the operator. It is an open problem, and if we take in equation 7, if we take instead of epsilon, if we take the function epsilon of t between 0 and 1/4, if we can obtain the similar results. So this would be some kind of comparison, let us say, result, and this is open problem. Now here are some references. So this is the 2 main papers of Irina Astashova. Here is our paper about asymptotic equivalence for higher order equations. Here is the result of Vanoky-Guradze and Sobol from 48. So this is all. Thank you for your attention, and let me to wish you Happy New Year 2022. Thank you.
Maybe I can add some remark about the difference between asymptotic equivalence, strong asymptotic proximity, and asymptotic proximity. I'll show you only a very simple example. Here you can see just wait a moment, something wrong with my presentation, but now I'll show you it carefully. Okay. I'll show you, where is it? Can you see it? Сейчас я ее заново открою. В этом моменте. Now you can see my not good quality paper, and you can see three definitions. The first one, as Susanna told you, the definition of asymptotic proximity. And the second one is the definition of strong asymptotic proximity of solutions. And the last one is the definition of the asymptotic equivalence of solutions to our equation. And I will give you only three simple examples for the case when n is equal to 1. The functions t and t plus 1 satisfy condition 1 and condition 3, but not condition 2. The function t powered minus 2 and t powers minus 3 satisfy condition 1 and 2, but not 3. And the functions 1 plus t powered minus 2 and 1 plus t powered minus 3 satisfy these three conditions. And if either the second or the third condition holds, then so does for the first condition. And this is the more strong definition in comparison of these two notions. And our talk was about this difference, and we obtained results, as Susanna told you, about all these types of proximity of solutions to our nonlinear equations at infinity. Okay.